Welcome, everybody in the lecture hall. Welcome, everybody on Zoom. Welcome, everybody from the future. It's 2024, and we don't need a green screen anymore. So let's get started on Spark. Actually, I will continue what I started last time, which was the initial version of Spark with RDDs. And then I will take you to data frames, them again, the same as pandas, and the same as those that we've seen as valid JSON. I have the feeling it was a bit loud, but so this is where I left you, right? So we have these narrow dependency transformations. So you remember these are the transformations like map, filter, all of those that don't have any spaghetti in there, right? That's every item in the outputs depends on just one item in the inputs. So what is really nice is that we can actually compose several of these transformations, but actually the way it happens is that it's a single stage, right? It's done in parallel. So here I put two transformations, but you see because of the narrow dependencies, you can all nicely parallelize it, right? So just so you remember what I told you, we have these executors that correspond to Yarn containers, but they're called executors in Spark. And then we have the slots that each correspond to a virtual core, might be double the number of cores if you use hyperthreading. So we usually imply the virtual cores. And that gives us here 4 slots. And you see that the tasks get dynamically assigned, meaning that everybody starts with 1 and whoever is finished first takes the next task and so on, right? So this is what we saw last time. Then comes the spaghetti, right? So not all of the transformations have narrow dependencies. Some of the transformations, a lot of them have this spaghetti in the middle. You can think of, I don't know, intersect or subtract or group or reduce by, join and so on and so on. So sort, all of these transformations basically have this huge spaghetti. And of course, if this is the way it looks like, that doesn't work anymore. What we need to do then is called, starts with an S. It's called shuffling. Yes, exactly. We need to shuffle. That's exactly what happens. We need to shuffle because since we have these wide dependencies in here, we have to send over the network everything that you need in order to make a calculation. What happens is that we create a new stage. So graphically, it means that you have a first stage which might have multiple transformations in there. Then you shuffle around. Then you have another stage, in that case, just one transformation. Then you shuffle around and so on. What is new compared to MapReduce is that in MapReduce, there was only one shuffle. There was a map transformation. You shuffle, there is a reduce transformation. But now we can get plenty of shuffling. So this is what makes it more universal and more generic than MapReduce. So it used to be with MapReduce that you needed 10 different jobs to execute something like matrix multiplication or something, or page rank. And now with Spark, you can just directly go ahead and have a single job that have plenty of shuffling in there. All right. So this is the general way that a job in Spark looks like. And again, you have to remember that the narrow dependency transformations get grouped together in the same stage. There's parallelism here, shuffle, parallelism, shuffle, parallelism. For whom is that clear? All right, that is the aha of Spark, the way that it works. And so typically, time elapses in this way. So typically, the entire Spark cluster is going to be executing that in parallel, and then it shuffles, and then it executes that in parallel, and then it shuffles, then it executes that in parallel, right? There is something called the Spark scheduler that takes care of orchestrating all of this. All right. And then, of course, you might remember that some transformations might have multiple RDDs as inputs, like Cartesian products, the join, all of this. So in that case, it means that we might have input coming from multiple places. We might have a first stage, a second stage, and then we take the output of this and the output of this and join it, right? For example. So it means there's a double shuffling here. There's this gets shuffled, this gets shuffled. Then you can compute the join. Nevertheless, you could still have a sequential execution in the sense that the whole cluster could do this, and then the whole cluster could do that, and then the whole cluster does that after the shuffling and so on, right? You can still have some sequential orchestration in there. I could also imagine, I actually don't know if Spark does that, but you could also imagine dividing the cluster in two, and half of the cluster does that and half of the cluster does that, right? But I don't know if this is actually done in practice, because you also have to consider where the data comes from, and it might be from all over the data nodes all over the cluster. All right, so this is basically a very generic way. So this is a layer on top. So you have these RDDs and transformations. So the DAG, the directed acyclic graph. And what I'm showing you here on that slide, you get by grouping the transformations into stages. So this is how you get this one. So now you have to, at first you get a headache with that, because like, how do these four things relate? Like a transformation, a stage, a task, a job. And so that can easily give you a headache, especially when people try to understand how transformations and tasks relate, but they don't relate. You really have to go through the stage to understand how they relate. So a stage is basically a vertical grouping of transformations, right? That narrow dependencies. Then a task is when you take a stage and you split it across the nodes, so like this, right? So you split the stage, the stage, but you realize that since the stage has multiple transformations, there is absolutely no relationship between these two. It's like cutting a wedding cake horizontally or vertically, right? So this is basically how that works. And then, of course, when you have a sequence of stages, so the whole DAG of RDDs, then that's the job. For whom is that clear? All right, very good. So what's very important to understand is that the two things that are logical are the transformations and the job. That's what the user sees, right? You're sitting in front of your Jupyter notebook, you write the transformations and you execute your job. This part here is physical. That is something that happens on the cluster, but the user doesn't even notice that, right? The advanced users, of course, would know, and they can adjust and fine tune, but the part in the middle is physical, right? So now I said that the advanced users understand a little bit what's going on, because that way they can a little bit adapt their query and try to make it a bit faster. So I'm going to give you a few tricks on this. So here's an example of DAG, right? So every rectangle in there is an RDD. It's a collection of values that is spread all over the cluster. And every blue arrow in here is a transformation, right? And I'm assuming that the one on the top was created with some creation function, like read from HDFS or uploaded from a list. And then I assume that there's going to be some action in there that is triggered. Remember that it's lazily evaluated. So if I just do this, meaning that in Python, I would just define transformations, nothing happens in the cluster. But the moment I call my action on RDD 10, let's say it's the 10th, then that triggers the whole computations on the cluster. Like the whole cluster gets into motion. And then finally, the results get, for example, downloaded to your laptop or written back to HDFS. But now imagine that I keep that, I'm still playing with my notebook and I'm done with that. And now I decide to trigger an action over there. Then it's going to re-orchestrate the whole cluster computations and so on again. And then I have this third action. Again, it's going to re-trigger the whole computations in there. Do you see anything inefficient in there? Yes, absolutely. You can cache basically all the part that is over here. So all of that part is common to the three. In fact, Spark will spontaneously do that. So as long as there's enough memory, it will try to hold it in memory unless something else replaces it. So if there's enough memory, it is going to cache. If there is not enough memory and you have more stages that execute more data and at some point the memory is full, then it's going to flush the memory to the disk, just like I showed you with HBase and with MapReduce. So that goes to the disk. Then it could be reloaded from the disk if you retrigger it. Takes a bit more time than from memory. But something even worse could happen. There's not even enough disk space, and then it even needs to be removed from the disk. What happens if it's removed from the disk? Then it gets re-executed completely and takes a lot of time. For whom is that here? Okay. And so the idea is that you have a way in Spark as a user to require explicitly Spark to cache something, meaning to give it a higher priority in the cache. That's called pinning. You pin the RDD in there. Like it's like what you do in UIs, right? You press a button and this one is pinned. And so that means that it should be a higher priority to keep it in memory. You can say if you want to keep it in memory, if you're fine, if it's offloaded to the disk, you can specify the level of caching that you want. That's called pinning. And then in that case, you have a higher guarantee in case there's computing jobs in the cluster, a higher guarantee that it's not going to recompute the RDD. This is why it's called resilient distributed data set. Resilient because even if you lose it from the memory, even if you lose it from the disk, you can just recompute it all over again. So it's resilient. All right, so this is one thing. There is another thing that you can optimize a little bit. It's that so of course, you want to keep the shuffling to a minimum. So that means that you can look at your DAG, you can look at the code that you wrote in Python to write all the transformations. Then you can ask yourself, okay, how many stages do I have? How much shuffling in there? Can I remove some shuffling? So sometimes just by thinking a little bit, you can reorganize your codes to have less shuffling. You can remove maybe some of the wide dependency transformations to have less of them. There is another trick, is that in some cases, you have a transformation that normally will require shuffling, but it doesn't actually require shuffling for the data as it is on the cluster. Can anybody imagine when that could be the case? Yes, maybe we can use the microphone.
Maybe if you want to sort the data and you know that the way that it is stored, it is already sorted?
Absolutely. If you already know that it is sorted and you want to sort the data, then there is no shuffling needed, right? It's already sorted. You don't even need to sort it, right? Something intermediate, imagine that the data is not sorted, but it is partially sorted in the sense that the data is organized in partitions. It's a mess within each partition, so it's not sorted within the partitions, but across the partitions, it's sorted. Imagine that you have, for example, words, English words with 26 letters, and you group the words in 26 groups, depending on the first letter of the word. And then you have a first partition with all the words with the letter A, a second partition with all the words with the letter B, and they're already partitioned in that way, right? So all the words with the letter A, they are together on some machine. The words with the letter C, they're together on some other machine. But within the machine, it's not sorted. So all the words starting with A, they are in any order. Who sees that this is basically the merge sort halfway through? You see that? So basically, we have partially sorted. What that means is that if that happens, if you know the data is already partitioned by the key on which you want to sort, then you don't need to shuffle. You can just sort locally within each partition, which is much more efficient, but without shuffling on the cluster. Who agrees with that? Awesome. And the same goes with grouping. If you want to do a group by, but it turns out that the data is already partitioned in some way compatible with the group by, you also don't need any shuffling. You just do some local grouping within every partition. The reason you can do that is that you never have a group that goes across partitions. All of the groups are contained within a partition. And one way to achieve this is explicit. You can explicitly pre-partition. You have ways in Spark to say, I want to partition the data in this and this way, right? And then Spark is smart enough to remember that you let it partition in that way, and then it's going to detect that it doesn't need to shuffle. Of course, that only applies if when you want to sort a group by, it corresponds to what it's partitioned by, right? If you partition in a way but sort on something different, of course, that doesn't work. Then you need to shuffle. So in that case, it's explicit. Sometimes it's implicit. For example, if you try to do a group followed by a sort, Spark might be smart enough. If it's the same key, you group by the same thing that you sort. It's a common pattern, even in SQL. You have a group by and an order by with the same keys. Then that will only require one shuffling, because after you have grouped, it's already pre-partitioned in this way. And in that case, you didn't say explicitly that you want to pre-partition, but it so happens that you've just done a group by, and now you do an order by. Who sees that in that case, you don't need to shuffle? Okay, think about it. Otherwise, that's basically the idea. So in that case, it would be implicit. But Spark is really smart with this thing. So imagine, for example, you have a join here, and the join key is such that that side is already pre-partitioned, then that you shuffle, and that you don't need to shuffle. It's already on the machines. Okay? So far, so good with the optimization. That's already a bit advanced. Many people using Spark do not even understand these things or go that deep. But if you do understand them, it allows you to do even better queries. Yes?
One question for the shuffling. Is it always all data to every node, or is it some kind of, okay, I'm going to need this data?
It depends. So let's take a few examples. Let's take group by. Do you agree that for group by, you don't need to send all the items to every node? You just need to send them to the node that corresponds to the bucket, right? So for group by, you just, the quantity of data that gets shuffled is linear. It's still quadratic for the communication because the machines connect to each other, but it's linear in the amount of data. Now you have other transformations like intersect, for example, or distinct. Right. So in these cases, these things would actually work. But there are cases in which the computation is such that you really need to compute an item out of all the items in the input. There might be more complex cases where this actually happens. And having this in mind, of course, helps a lot. Right. Did I answer your question? Awesome. Any other question before we proceed to the cool part? No other questions on Zoom? Any questions? Nobody seems to be raising their hand on Zoom. All right, lots of people on Zoom. All right. So let's move to data frames. So a bit of history. In the original version of Spark, that didn't exist. There was just RDDs. And then somehow Spark started to get a reputation that it's slow. It's like XML, you know, it started to get the reputation that it's complex. And Spark started to get the reputation that it's slow. And so the idea is that in some cases, the data is such that you can store it in a more optimal way in memory. And it is such that you can also shuffle less if the data takes less space, right? So you can optimize a little bit. But now if you think of that, we've already discussed that. We've already discussed that a couple of weeks ago in the data modeling lecture, where I told you that there is a specific case in which we can compress the data in memory. Do you remember what it was? So of course, there's a big word on the screen that indicates what I want to say, but in what context was that? Imagine I have a collection of JSON objects. When could I optimize? Yes? When they are homogeneous, exactly. And formally, when they are valid against the same schema, and the schema is not too exotic, meaning that there is no open object types, all the types are concrete and so on, right? In that case, you can indeed compress it. And the key part is that we get a data frame. So when you have a valid collection, a collection of valid JSON documents against some schema, it's not too exotic, then you can actually represent it as a data frame. What this means concretely is first, you can save it as a Parquet file or some more optimal format, takes less space on the disk, also less to read from the disk. But that also applies to Spark. It means that when you have this RDD of JSON objects, then who sees that the RDD of JSON object is going to also take much less space if that JSON is valid and we can store it as a data frame? Who sees that? Right? For example, the JSON keys don't need to be repeated, right? If it's the same schema everywhere, then you don't need to repeat the key. You already saved half of the space like this, right? Then if everything is an integer, then you can save it as a 32-bit or a 64-bit integer, right? Instead of as a string and so on and so on. So this is how later in the evolution of Spark, they added the data frames to the system to account for that case and make it faster in the case that the data you're manipulating is highly structured. They did not remove the RDDs. The RDDs are still necessary if the data is heterogeneous, right? So they are still there. But if the data is structured, then we can do better than that. And so the way you see that, where that comes from the user's perspective, is that if you want to query a text file, then of course you get an RDD of strings, and then you can define your functions. Remember the lambda, that's the filter transformation function. You deal with strings. But if your file is not just text, but it's a JSON lines file, so there's one JSON object on every line, here we have an impedance mismatch. It's that Spark doesn't understand that, doesn't understand JSON. Spark just sees strings in that case. So it's an RDD of strings. So what happens is that when you're going to open that JSON lines file, that's read as an RDD of strings, and then the user, and I insist, the user, not Spark, the user has to explicitly write parse JSON, which maps the RDD of strings to an RDD of JSON objects. But now the JSON objects are really Python dicts. In that case, if you use Python, then you filter. And again, the user has to use the Python syntax on the dicts to basically look up and so on. So now you basically write Python in there. But you see that it's a bit cumbersome because the user has to take care of this because Spark doesn't understand JSON. So it's up to the user to actually parse it and so on. So it's actually not so nice. And so what data frames bring to you is something a bit more convenient that does it a bit more natively. And the idea is that a data frame can be seen as an RDD of rows. Give you a few seconds to digest that. A data frame is an RDD of rows. That's the same thing as saying that a table is a collection of rows, right? It's a collection of records. So a data frame is an RDD of rows. And these rows all have the same attributes, but they could be nested. That is not forbidden. That's why we call it a data frame and not a relational table. Okay? So it means that if I take one item in my RDD here, that's a row, one single record with attributes mapped to values. If I look at the whole RDD, then I get the entire table or the entire data frame if it's nested. Okay? Something that shouldn't surprise you because I've already explained that is that when you have a data frame, the way that it's stored in memory is by columns. So if you have, let's say, 5 columns in your data frame, then this column is stored together, this one is stored together, this one is stored together. In every partition, of course. If you have plenty of partitions, then that's by partition. In every partition, this is together, this is together, this is together. Right? The same goes with Parquet. When you have a Parquet file, if you look at the way it stores it on disk, it's all grouped by column. What is the benefit of that? Is that if there are columns that you do not use, it's very easy to get rid of them. If you read a Parquet file and some columns you don't need, then you don't even read them. And if they are stored together on disk, it is very easy not to read them. For whom is that clear? For whom is that not clear? Okay, more hands. That is called pushing down. We push down a projection. Getting rid of columns, that's called a projection. And if we don't even read the columns from the disk, that's called pushing down the projection to the moment you read it from the disk. That is the secret to make things fast in big data. You push down, push down, push down. You try to get rid of all the data you don't need as early as possible. And if you cannot even read it in the first place, even better. It makes it faster. So that's why columnar storage. So another aspect, as a consequence of that, is that if you store RDDs of Python dicts, for example, it's going to take a lot of memory. But if instead of an RDD of Python dictionaries, you have an RDD of rows, like data, oh, I'm disapparating. That is so cool. You know, you can fly in your dreams. Now I can just apparate and disapparate on the screen. Anyway, so the data frame here is going to take less space in the memory. So this is something we appreciate because it's going to be faster. Plus, we can fit even more data with the same resources. All right, here's a concrete example. So this is the data frame version of that, but that now with data frames. So the first thing you see, so it's not called RDD anymore, it's called data frame. This is something different. But now you see it's native. You can directly say, read that JSON and put it in a data frame. How? I will tell you soon. But basically then what happens is that since you have a data frame, you can use SQL. And so it means that you can create a view, give it a name, and just drop your query in SQL. You don't even need to bother with transformations or anything, just write down SQL. So this is a dialect of SQL called Spark SQL, has a few features that are specific to it, but this looks very much like the SQL that we've seen at the beginning of the semester, right? And then, of course, once you have executed your SQL, then you can in that case, take the first 10 results, for example. You could also do it in the SQL, right? I could also put limit 10 in the SQL. They even support offset now. It wasn't supported a couple of years ago, offset. We were missing it, but now they've added offsets. So you can use limit and offsets in Spark SQL. All right, so now you see why SQL is useful, why it's still useful at large scale. So there was a long period of where nobody liked SQL anymore, and everybody loved APIs and so on and so on. But now somehow in the past 5 or 10 years, SQL made a huge comeback, and now suddenly everybody loves SQL. All right. Now, how do we read from a file? So the idea is that you can read JSON, CSV, there's plenty of formats that it can read, Parquet also. But then comes a natural question, if you read CSV or JSON, how do you know the schema? Because if you have a data frame, you need a schema. So how do I know the schema? Well, the answer is it guesses it. It tries to infer the schema from the data. For example, imagine that you feed Spark with a CSV file. It means that you would have spark.read.csv here, and you feed it with that CSV file. Remember that the first line has the headers, then you have the values. Now, Spark will notice that the first column seems to be an integer, and the second column seems to be a Boolean. There is a cost. There is a cost to it, because in order to guess that, Spark needs to actually look at the data. So it will have to scan over the data and look what it looks like, right? So it takes a bit more time than just opening an RDD with text file. That one is much faster. But if you accept the small overhead of inferring the schema by scanning through the data, you get back the benefit of a faster query. So it's always, there's no free lunch. If you have a benefit on one side, you need to pay it on the other side. And this is why you pay it. Yes? Yes, you can. Absolutely. So I'm repeating for the microphone. If you already know the schema, you can tell Spark what the schema is, and then Spark trusts you, right? You override the whole thing, and then that's much faster because Spark doesn't need to discover the schema. It's just going to do it as it validates as it reads the data, right? I guess you get an error, but I think we have never checked that. We should check. I think you should probably get an error. It probably complains if it trusts you. And then if you betray Spark and give it a schema that actually doesn't correspond to the data, then Spark is going to complain. Okay. All right. And in fact, that is also a recommendation. If you do know the schema, you should give it because it makes it faster. So this is what you mentioned is yet another optimization to make it faster. Note that with Parquet, you do not need to give the schema. Why? It's already in Parquet. The Parquet file already has the schema. So this is also something to have in mind. But in CSV or JSON, there is no schema. So you need to do it to give it as an extra parameter to the function call. All right. And so you can basically squeeze this CSV over there in that data frame over here. Same with JSON. You see how super inefficient it is. You're repeating that all over the place, takes a lot of space. So either it infers the schema, noticing it's an integer, it's a Boolean, can also do it based on samples, or you can give it explicitly in JSON, it JSOunds that would be foo integer bar Boolean, for example. Of course, it doesn't understand JSON, probably JSON schema, or maybe an API-based way to specify a schema, data frame schema, and then it turns it into this right there. Okay. Now, there are people who don't like SQL. Who likes SQL? Who doesn't like SQL? Okay, it's fine not to like SQL. And that's okay, because then you have here data frame transformations. So if you love APIs, it's not a query language, it's an API. But if you love APIs, you can also write your query in this way, filter, sort by, select, take. But you need to know that this is not the same API as for RDD. It's a different one. There's RDD transformations, and there's data frames transformations. So you have to learn all of the methods and so on that are not the same as for RDDs, even though it resembles it a little bit. It's a little bit involved in the way the syntax, I mean, takes a little bit of time to getting used to it. But of course, if you know a bit of pandas, maybe that makes it a bit easier. So it's more involved. But if you prefer this, then this is totally fine. In fact, at the exam, we even give you the choice, right? If you can either use SQL or the data frame transformations. All right, so everybody is happy, right? You basically can pick what you prefer. All right, then we have, yes, the types. So now you probably get bored with my type mappings, right? I keep showing you type mappings, but what I'm essentially telling you is that it's always the same. And here again, it's always the same. Because if you look at the available types in there, it's going to look pretty much like what you have in JSONic, in Parquet, like in all the others. So you see, for example, you have byte, short, integer, long, float, double, decimal. So that's how it's so the numbers that you can have. You can have strings. You also have varchar and char, if you like, again, SQL types, Boolean, binary, like blobs, timestamps, date, and so on. So there's a few types like this. So these are the atomic types, right? All the atomic types. Plus the structured types, you know, always the same. At the very least, there's going to be an object and an array type. They might not be called this way, but there's an object and an array. The array, that's great. It's called array. The object, in fact, is struct. Struct corresponds to a JSON object. Map, it exists, I told you, in some of the data frame or schema validation libraries or the formats, data formats. You typically have a third kind of structured type. The difference between struct and map is that in a struct, all the values must have the same type, and the keys can be something else than strings. For example, you could have a map from dates to integers, right? It's not JSON anymore, because in JSON, it has to be a string, the key. But in maps, the key can be any atomic value, right? So this is the difference. So you have to consider this one as a little bit of an extra available type that doesn't map to JSON, but some of the formats have it. But array and struct map to JSON. So if you open a JSON file, then that will map it to array and struct, the objects and the arrays in JSON. And then there's also a mapping here. And basically, now if I take it to the next level, so this is just the list of the types I have in data frames. And what I did, guess what? I just couldn't resist. This is what I did. I had to do that. So now you have all of the data frame types that basically are part of the data frame API. This is how they map to Java. It's official. You can find it in the documentation of data frame. That's the corresponding Java types. You have the Python equivalence. I warned you, float double in Python, called float. Int catches everything in Python. It's all integers and so on. And in JSONic, you have also these equivalents over there, right? So these are all the correspondences. But again, you can see it's always the same boring list of types that you have everywhere. So it's really just like I told you many times, it's like the Swiss dialects, right? You just understand them all, even though it's different in different words. So that was for the atomics, and that's for the objects, right? How it maps. So the arrays are lists in Java and lists in Python. The maps are maps in Java and dicts in Python. Structs maps to, it maps in a strange way, actually. I never exactly got why they did the mapping in this way, but they actually mapped the maps to dicts and the structs to lists or tuples. It probably has to do with the fact that the dictionaries in Python are more flexible than JSON objects, and probably they would accept other kinds of keys. So maybe this is why. And the way we map it in JSONic, so here, why don't I appear? Yes. So arrays map to arrays and the objects map to structs. At least in RumbleDB, this is how it's implemented. So whenever you have an object, it's running as a struct type. Okay. So yet another restaurant menu. So you see you have JSON, you have Parquet, you have CSV, you have text. If you want just a column of strings, you have JDBC, that's for connecting to PostgreSQL. So there's what's called connectors, and you can connect Spark to whatever you want. So this is to connect it to PostgreSQL. You can connect it to MongoDB. You can connect it to many different systems. Some of them are hard-coded statically. You see what I mean with static? Statically, because that's a method call that's known at compile time. So these are all the known ones. And there are some formats that you can load dynamically, but then of course you cannot know them at compile time. And in that case, you just supply them as dynamically in the format, right? For whom is that clear? All right, so these are some of the formats, and there's many, many, many other formats. But what's really great is that once you have done that, you get a data frame, and then you can use Spark SQL or data frame transformations. What then happens is magic. You don't need to worry too much about it. What's going to happen is that the data frames are physically, in fact, RDDs of rows. So they are really handled similar to RDDs in the system physically, except that now it's hidden. And your plan that you get out of your SQL query or out of your data frame transformations gets mapped to a physical plan on RDD transformations, this RDD right there. But again, everything that's below here is automatic, and you don't need to worry about it. You only think in terms of data frames and Spark SQL or data frame transformation. And the benefit of that, this, you probably recognize data independence in here. In fact, we have we don't have any here. So basically, if you draw a line in here, like you draw a line here, this is data independence, right? That's the data independence line. And once you have the data independence line, you can start throwing optimizers and all kinds of architectures that are known from relational databases. And so what you send with your SQL query or your data frame transformations goes through a very complex pipeline that is worth several scientific publications in various conferences, and it goes all the way to RDDs. And it figures it out, basically. It will find out the optimal way to put the transformations. Did we have questions? No questions? All right. A few minutes until the break. Now let's look at Spark SQL. So first, Spark SQL looks like SQL, right? If you look at this, there is nothing surprising. Select from where, group by, having, order by, limit, and offset. This one I was able to add because now it exists. So this is basically classical SQL. There's absolutely no surprise in there. I made a few annotations here. Is that there's shuffling. As you can imagine, now you can already imagine the RDDs that are behind that. We have to shuffle when we group by, and we have to shuffle when we order by, except if the key is the same. If that's the same key here and here, then you only need to shuffle once, and here there's no shuffling anymore because it's already there. Now, think a bit of the transformations, because we've already seen that in the previous weeks. This here, do you agree it's narrow dependency? That's a projection that you can do in parallel on all machines. The reading is also in parallel. That's the HDFS blocks, or it's already spread over. Where is a selection? That's also a parallel. It's a filter transformation. Who agrees? Right? So this is also in parallel. Group by, we need to shuffle because we need to bring together the values that have the same key over there. Having is without shuffling, because you just do it in place. You have the groups spread over the machines, then you keep them or you don't keep them. So that's, again, narrow dependency. Order by requires a shuffling if that's a different key, and you cannot optimize. But in some cases, it's no extra shuffling if it's the same key or a subset of the key, right? And here you can also have the same changes in here, desk, nulls first, and so on. And limit and offset. So limit and offset, they look like uninteresting and trivial, but it is incredibly difficult to implement on top of a cluster. There is, in fact, a transformation on RDDs that you basically kind of need to do these things. It's a transformation that's called zip with index. What zip with index does is that out of an RDD of values, it associates every value in a pair with an integer. So if you have the RDD foo bar and so on, it will do foo1, bar 2, and so on. So a pair with the value and its position, 1, 2, 3, and so on. once you have used zip with index, then do you see that you can implement limit and offset with a selection on the position? You basically select such that the position is here between 10 and 110, plus minus 1, right? Between 10 and 110. Who sees that? Imagine zip with index, you add the position, and then you filter with limit and offset, selecting on the position. Now you have it. But zip with index is hard to implement. In fact, it's so hard to implement that it doesn't even exist in Spark SQL. You have it on the RDDs, but you don't have any zip with index in Spark SQL transformations. But there is a trick because we needed it for RumbleDB. So what we did, of course, is we went to Stack Overflow, and there was a Stack Overflow page in which somebody came up with an implementation of zip with index in Spark SQL. So we kind of made it work. All right, the break. I still have a few minutes. So this here SQL was made for tables, flat tables, right? But in practice, in data frames, you might not have flat data. An example of this is that a column here might be an array of strings. So here I put the JSON way. I could also have drawn it as a data frame in the way that I did it 2 weeks ago. Just wanted to keep it compact, right? But I basically have these arrays of strings right here. And what I can do is use the explode function that is going to basically normalize, put it in first normal form. You remember the first normal form? Everything atomic. And in order to normalize it, the costs that you need to pay is you duplicate the values here. So what Albert Einstein was only once, now you have Einstein, and you just duplicate it with each one of the values that came from the array. For whom is that clear? Right? So this is called, that's a normalization algorithm. That's how you normalize into the first normal form. And it turns out that here it's implemented with explode. It doesn't exist in SQL. You don't have it, at least not in the early versions of it. But this is really a Spark extension that does this thing on the right. Now, from a language design perspective, you have to be very careful because normally in a functional language, when you have a function like that, it should only act locally. So normally that should return something out of countries. But somehow this explode function has a non-local effect on this one here that has nothing to do with this function call. It's outside, and yet it has this effect. So this is why I like to call a spooky action at a distance as a reference to quantum physics, but this is basically what happens here. It's not really a function. It's a function that kind of modifies the tables around it. For whom is that clear? All right. Now, if you want to do things more complex, you can do the same thing with what's called a lateral view. So a lateral view is something that comes in the from clause. You basically say that you have the table here and you kind of join it with itself. It means that you take that table and you join it to some virtual table obtained from flattening that. So it's like a join, but with itself. And this is what you get here. And the beauty of doing it in this way is that you know that when you join, you can join again and again and again. So you can chain the joins. So here too, you can chain the lateral views in there. So if you have nested and nested and nested, so like a dream in a dream in a dream in a dream. So here you have, again, objects in arrays and so on. Then you can just have 2 levels of unnesting here with 2 lateral views. Okay, who understands that? Who doesn't? That's great news if you don't. Because in fact, this is the limitation of data frames and Spark SQL, because SQL was not designed for nestedness. And this is the reason why now that we are trying to push SQL to its limit to handle nestedness, we start seeing that it's hitting its limits, right? So that was arrays for objects. You use dots, right? So you just extend SQL with dots in here. So name dot first. And that extracts the value in here. That shouldn't really surprise anybody that does object-oriented programming, right? It's kind of the same way you would do it in many languages. Okay, who understands this query? Very good. So it extracts first and last, puts them in columns in there. And I'm just waiting for it to ring because I'm pretty sure it's going to ring again in the mid. I'm almost done with the slides, but I'm pretty sure, yeah, you saw. So I'll finish this in after the break. So I'll see you at 3:15 for the continuation.